Welcome to Dragon Mathematics. I'm Dragon, and this is the mathematics. This video is about law of sines. The first thing I want to do is just prove it, show you how we get the law of sines. It looks like this. So we have a triangle that is not a right triangle, okay? And we'll say angle A, angle B, angle C. Try to make the C more noticeably capital here because of that lowercase there. So in this triangle, which is not a right triangle, this is the case. Sine of A over side A is equal to sine of angle B over side B is equivalent to sine of angle C over side C. So visually you can see that that's saying that the ratio of this angle to this side is equal to the ratio of this angle to this side, but how do we get there? So what you do is you'll turn this non-right triangle into two right triangles by bisecting this side C here. And we'll call this H. And so now we on triangle 1 over here on the left, just using our basic trig ratios. So Katoa, we can say sine of A is equal to this opposite over this hypotenuse, right? Sine of B is equal to this opposite over this hypotenuse, right? And so if you rewrite this, multiply the B on both sides, we'll have B sine A equals H. And same thing here, we have A sine B equals H. And so these are both equal to H, which tells me that B sine of A actually equals A sine of B, right? And then put the A over there, put the B over there, and that's how you get that portion. But then we're wondering, well, where's the C? It is done like this. A weird little trick we do for the proof is we'll say, okay, and what if we extended this side, right there, to where it actually turned this whole triangle into a right triangle? See, we love right triangles, so we're always trying to manipulate it into a right triangle because we know so much about it with Pythagorean theorem and trig ratios. So once we do that, we'll call this H now. And then this angle right here, okay, is actually 180 minus C, right? Because this horizontal, a straight line like this, is a angle of 180 degrees. So that horizontal right there is 180. This is C. This is 180 minus C. So now working with this triangle, I'll say, okay, sine of this angle, 180 minus C, is equal to opposite H over hypotenuse B. And then I'll look at this angle B and say sine of B is going to be opposite H over the hypotenuse here, which is C, little c, right? So we've done it again. We have, if we rewrite this, B sine of all this is equal to H, and C sine of B is equal to H. So they're equal to one another. Yeah. And then the last little trick we pull is I just know that this 180 minus C here, when you're taking the sign of that argument, it's actually just the same as sine of C, which might seem weird, but we'll prove that too, right? It's because if you look at the unit circle, right, and go over here, we've kind of shown this inadvertently before other videos. Say I just take my angle 30 degrees. I'm just choosing an arbitrary angle to demonstrate this. I know that these coordinates here are root 3 over 2 and 1/2. And so what if I choose the angle C to be 30 degrees in a hypothetical? Well, then 180 minus C, so this horizontal, minus 30 degrees. Well, that's just going to be that horizontal with this little piece removed, which should be what, 150 degrees. And at this point, the coordinate is negative root 3 over 2 1/2. Okay? Remember the sine of the angle is this y value. So look at that. They have the same height and they have the same sine. So that's showed that if I see sine of 180 degrees minus angle, I also can just write that as sine of that angle. So I'm going to actually do that. I'm going to take this, put it there, and write b times sine of c equals c times sine of b. I don't know, my sine s's have been getting so big recently, I don't know what happened. And same here, this goes over there, this goes over there, because of algebra, right? Divide this by c, so sine of c over c, divide this by that b, sine of b over b. And we know that sine of angle A over side A equals sine of angle B over side B. And that means if we have sine of angle B over side B here, then we can just finish it off. That's your law of sines shown to be true. Okay? So there it is. That's how you get that. And why is it useful? Say I have this triangle right here labeled A, B, C, and B side is equal to 12 units. Angle A is equal to 35 degrees, and angle C is equal to 70 degrees. And I'm looking to find the other missing sides and the angles. So what's A, what's B, what's C, what's angle B? First thing I'm going to do, it's easy, is I have two angles of this triangle. A is 35 degrees, C is 70 degrees, and so there's only one angle left. That means if A plus B plus C is 180 degrees in a triangle, well then we have 105 from adding these together. So 35, 70 plus what? We have 180 minus 105 equals 75. So that was easy. I'll fill this out. B is 75 degrees. And so then now we'll use the law of sines. So I'm going to write it like this. Sine of A over side A equals sine of angle B over side B equals sine of angle C over side C. And I'm going to fill in what I know, which is this angle right here. A is 35 degrees, so sine of 35 degrees over side A equals sine of 75 degrees over, what was side B, 12, equals sine of 70 degrees over C. Right, that's our law of sines rewritten with the values that we know substituted in. This right here is a good indicator of I need to use this to solve things. It is just a number, so the sine of 75 degrees is a value, 12 is a value, so this ratio is just a known number. And I'm going to use my calculator for that. Okay, so let's punch this into the calculator. It's degrees sine of 75 degrees, and we'll divide that by 12. Approximately 0.0805, we'll call it, right? And so the next step would be to say, okay, well, these things are all equal. That's equal to that. That's equal to that. So that means sine of 35 degrees over A equals 0.0805, okay? And you can move this over here. So A is equal to sine of 35 degrees over 0.0805. I think I covered that in the last video, why that's allowed. So I would take, let's see, sine of 35 degrees, divide it by the value we got there. And so we'll have approximately 7.1257 is A. And we do the same thing with the sine of 70 degrees over C. That's also equal to 0.0805. And same trick, I'll say C is equal to sine of 70 degrees over 0.0805, which equals approximately what? Sine of 70 degrees divided by 0.0805, approximately 11.6732. So that means our triangle is completely solved. And that would be the triangle all solved up. So let's do another example of how to use law of sines. So now let's say we have this triangle where this is what's given. A is 30 degrees, B is 45 degrees, side A is 10, and the problem wants you to find side B. Well, then we'll set up the law of sines. Sine of A over side A is equal to sine of B over side B is equal to sine of C over side C. Okay. Sine of 30 degrees over 10 is a number. Sine of 30 degrees divided by 10. All right. So now we have an equation that says sine of 45 degrees over side B is equal to 0.05, and the same is true for sine of angle C over C. We're just interested in finding B, so we will do this equals sine of 45 degrees over B. Remember, you can move this over. So sine of 45 degrees over 0.05 is equal to B. I will find out what that is. Sine of 45 degrees over 0.05. So B is approximately 14.1421. All right. And yep, it's just asking us for B. So, if you would have set it up and used this part of the equation, and you wouldn't get B, obviously. So you just have to see what you're asked for, see what angles and sides you have, and then pick and choose which pieces of law of sines will help you accomplish that. And so this one's done. So say we have another triangle like this one, where the angles are, say, D, F, G. Originally I used E, but we're not supposed to use E because E is approximately 2.718 Euler's number. I don't want to use it here because that's could be confusing. So that's why E is skipped if that seems weird, but D is equal to 8 units, side F is equal to 10 units, and angle D is equal to 25 degrees. They tell us to find angle F. So I would set this up using what I know, which is that sine of F over side F equals sine of D over side D, and then substitute in the known quantities, leaving me with sine of F over 10 equals sine of 25 degrees over 8. And I'll just do a quick cross multiply is what we'll do. So 8 sine of F equals 10 sine of 25 degrees. Move that 8 over there by dividing both sides by 8. Sine of F equals 10 sine of 25 degrees over 8. And this is just a number, and that number is 10 sine of 25 by 8. That number is 0.5283 approximately. Okay. And we know from our previous video that if we want to pull the F out of here, because our goal is to find the angle F, well, then we have to say F is approximately equal to inverse sine on this number. And I'll just do that in the calculator by reselecting it so we get a more exact answer. The angle is approximately 31.88, approximately that in degrees. And if you so choose, we could also say, well, what is it in radians? That is approximately 0.5566 radians. And that would do it for that. All we had to do was find F, not too bad. So you saw what you have to do. The law of sines allows you to analyze a triangle, look at, even if it's not a right triangle, you can look at what angles you have, what sides you have, what angles you don't have, and what sides you don't have. And then based on the given information and based on your law of sines, set up the problem in a way that makes sense, right? This was also true in part of the problem, but it's just kind of extra information because we didn't need to use side G or angle G. So just use the portion that you need from law of sines and solve it. The cousin of law of sines is, of course, the law of cosines. which comes up a lot in physics, engineering applications. At least that's what I have experience with. Probably use law of cosines a bit more than the law of sines. When you want to find, say, this angle C, right, we're doing something similar to the setup for the law of sines, but this one takes a little more algebra and toying around with it to get it where you want it to be. So if this angle is relevant in your physics problem, right, and you know a few other things, well, in order to find what the side C is, you're going to need this formula, which of course we're going to derive cosine of C. Okay, so see, it kind of looks like Pythagorean theorem right here, but this part is sort of just telling us, and since it's not a right angle, we subtract what? 2 times the magnitude of A times magnitude of B times that cosine of that angle right there. It's often written like this because, again, you want to find C. Okay. And so how do we get to it? Well, first thing I do is turn it into 2 right triangles again. Right? These are right triangles. And then I'm going to call this height here H. This distance from here to here is G. Name this distance from here to here F. I can write a few things down that are true that I know about each of the right triangles, right? So this right triangle here on the left, we can say, okay, this is like a squared plus b squared equals c squared, but for the new right triangle we made, so g squared plus h squared equals c squared, because look, g squared plus h squared equals c squared. We know that's right. Okay, and so now this g is equal to this distance a minus this little piece f, right? So we'll just write a minus f. And what I'm going to do is go over here and look at the other right triangle we have. And some true things that I can say about it are what? Sine of C, this angle, is opposite over hypotenuse, so equal to h over b. And the correlate of that is that h is equal to b sine of C. And we also have the Pythagorean theorem that's relevant on this side. So f squared plus h squared equals b squared. Then I'm going to plug the h in. So I'll say f squared plus b sine C, quantity squared, equals b squared. All right, so you see what I did there? I found h, wrote the Pythagorean theorem, put the h squared in there. This is, if you write it out, distribute the second power. You have that. And so now I'm going to use that to go back and finish writing my Pythagorean theorem based on the left side right triangle there. So g squared, let's rewrite this with the things we know now. G squared is a minus f squared plus h squared. Well, h is b times sine of c. So I'm just going to write b sine of c squared. And that equals little c squared. Okay. And we also were able to find f from our adventures over here. I did not write it, but you can solve this for f. So I'll say f squared is equal to b squared minus b squared sine squared c. Right, just a little algebra. Move that over this side of the equal sign. And that means f is equal to the square root of b squared minus b squared sine squared c. Okay. So now I know f, and I'm not going to plug f in at this point because that would be a little annoying to work out. So what I'm going to do is expand this quadratic, which is a squared minus 2af plus f squared. So that's that piece. Plus, I'm going to distribute the squared for this. So b squared sine squared c is equal to c squared, little c squared over here. Now we can put in this f, and it's going to get a little cluttered perhaps, but it'll work out. A squared minus 2af, where f is this value, square root of b squared minus b squared sine squared c, okay, plus f squared, which is b squared minus b squared sine squared c, plus b squared sine squared c, right? Because I distribute this squared boom, boom, equals c squared. So an easy step to take here is to say, look, I have a minus b squared sine squared c and a plus b squared sine squared c. Real easy. I know that that's equal to 0. So let's rewrite it to a square root of b squared minus b squared sine squared c plus b squared equals c squared. We're getting closer. So you can see at this point we had everything in terms of a, b, and c, which is our goal. And so now the next step is a little funny, I suppose. You take this part inside the square root, and I'm going to pull out a b squared. Why would you do this? Well, it's because we want to prove law of cosines to be true. And so you see how you can do that. See the b squared distributes. So b squared times 1 is b squared. B squared times negative sine squared c is negative b squared sine squared c, all in the radical square root. So that's what we have. What's also doable is to say, well, if you have two things multiplied by one another inside the square root, that's the same as having two square roots like this, right? Just being multiplied together. And then this b squared under the radical, well, the square root of b squared is just b. So I could take this whole piece, change it into b times the square root of 1 minus sine squared c. Another thing is this piece right here is one of the first trig identities that we looked at, and it is that cosine of x is equal to plus or minus the square root of 1 minus sine squared of x, and sine of x is equal to plus or minus the square root of 1 plus sine squared of x. And so we're going to use this one and just replace it. And there's a lot of seemingly arbitrary substitutions going on, but this is what it takes to show that law of cosines is true. So I'm going to put that there. Cosine of c comes out quite nicely. So this piece right here I brought down. So I'm going to now have to bring this down. I'm going to say a squared minus 2a times, here I should put the b here as well, times b times cosine of c plus b squared equals c squared. We just have to sort of clean it up a little bit by writing it this way. A squared plus b squared minus 2ab cosine of c. And to rewrite that, we can if we choose. I'll just copy this. We can write it like that. And that's your law of cosines shown. Okay, cool. So let's look at reasons we want to use law of cosines. Why do we want to use it? Well, say we have this triangle, which is not a right triangle. And the known information is that A is 7, side A, side B is 9, and angle C is 60 degrees, and we're asked to find side C. So all we have to do is set it up, right? Plug in what we know. C squared we don't know. A squared is 49. B, if you square that, is 81. Minus 2 times A is 7, B is 9, times cosine of 60 degrees. So calculator time, we'll do what, 49 plus 81, 130 minus, that's 63 times 2. I'll subtract 126 times cosine of 60. Actually, I can also just find cosine of 60. Cosine of 60. So 126 times cosine of 60, which we just found, is 1/2, 0.5. And half of 126, 63. So 130 minus 63 is going to be our c squared. So c squared equals 67. That means c is the square root of 67. Approximately 8.1854. Pretty useful. Just plug and play. Easy stuff. So another one, I decided to write with J, K, and L because you'll see different labelings, different variables, and it's good to be used to just solving them. Don't panic. Okay, and what's given is side J is equal to 13. Side K is equal to 20, side L is equal to 25, and they want us to find angle J. All right, so law of cosines, J squared will equal K squared plus L squared minus 2KL times cosine of our angle that we care about. And plugging things in, 13 squared is 169. 20 squared is 400. 25 squared is 625 minus 2 times. All right, and so j squared, that's 13 squared is 169. 20 squared is 400. 25 squared is 625 minus 2 times 20 times 25. Well, let's see. 2 times 25 would be 50. So 20 times 25 is 500. 500 cosines of j. Okay. And then what is it? This is 1025. I'll subtract it from both sides. So 169 minus 1025 is equal to negative, that's 1000 cosine of j. And 169, I just did it, but 169 minus 1025 is negative 856. And that's equal to negative 1000 times cosine of j. So divide both sides by negative 1000. This should be what? 0.856. Verify that on the calculator and say negative 856 divided by negative 1000 is 0.856. So we're going to do the same thing here. We need to use inverse cosine to find the angle J. So inverse cosine of 0.856. Can't do that in my head. 0.856 will give us approximately 31.1296 degrees. Again, that's approximately equal to this many radians, 0.5433 radians, right? So we did it. We took what we were given. We applied what we know, which is the law of cosines, and plugged in the values and calculated the angle J. Good stuff. So just to be thorough, we have one more demonstration of law of cosines here. We have a triangle with angles PQR, and we're given this. Side P is equal to 10, side Q is equal to 12, side R is equal to 15, and we're told to find Q, the angle. So we don't have any angles, only sides, and that's not a problem. If I'm looking for the angle Q, I'm going to put, you can move anything you want later, but I just like to set it up this way. So I'm going to put the side Q squared over here because that will make it work out nicely for us. So here's our law of cosines for this problem. And so we plug in 12 squared, 144, 10 squared, 100, 15 squared is 225. And minus 2 times PR, which is 2 times 10 times 15 is 150. So same deal for this one, it's plug and play. This is 325, 144 minus 325 equals, this is negative 300 cosine of Q. And if I do 144 minus 325, we get negative 181 there. And so I'm going to divide both sides by negative 300. That gives us cosine of Q. Divide by negative 300. Cosine of Q equals 0.603. Repeating. I always like to be accurate. Say that. And so that means Q is approximately equal to inverse cosine of that number, which we're going to plug in straight to the calculator. So Q is approximately equal to 0.9231. I think I left down radians. So again, make sure you know what mode you're on, so you know what numbers you're reporting. It's also approximately equal to 52.8910 degrees. That's our Q, and that does it. Right, so law of sines is useful when you know any two angles and any side. And then our law of cosines, that can be used as we saw in the example if you have three sides or if you have two sides and an included angle, meaning you have this side, and this angle. And that covers that. So I hope you enjoyed this video. I'll see you in the next one. Bye-bye.